All right, so um, hopefully you have realized, hopefully you have understood. I must have said this before as well. Anytime we are working on chemical synthesis of any kind and we are generating some chemicals, essentially we want to maximize the efficiency of the reaction. That means that we want to generate a maximum amount of product and minimize the cost for running that. And this can be achieved if, of course, the reaction, let's say your general reaction that we have been discussing so far, A moles of A reacting with B moles of B, giving you C of C and D of D. So if you have more products in your reaction mixture than your reactants, and if you are able to achieve that at mild temperature and pressures, that's a good thing. Now, on the other hand, if your equilibrium mixture has a different ratio, that means it has more of A and B and less of C and D, that's a problem right there, and something will need to be done to tweak the reaction conditions so that the equilibrium moves in a direction that the extent of the reaction changes and the yields become better. And one of the ways to do that would be, or some of the ways rather to do that would be that you could change temperature, you could change pressure, you could change volume and the concentration, and that would essentially change the equilibrium of how or where the equilibrium lies, and so you would be able to tweak the reaction conditions a little bit better depending on the nature of the reaction. So in the next slide, so in this particular section, this is the part that I'm going to discuss. This is what Le Chatelier principle is, that if there is a stress that is applied, and when I use the word stress, I mean change due to concentration, change due to volume, change to pressure, change to temperature. Why are we bringing about this change? We are bringing about this change because we want to improvise our reaction conditions. So according to Le Chatelier principle, if a stress is applied to a reaction mixture at equilibrium, the net reaction will occur. It will go in a direction that undoes the effect, so it relieves the stress. So what that means is the reaction will occur in a manner that the reaction will move in such a direction that a new state of equilibrium will be achieved. So any disturbance that you cause, let's say A moles of A plus B moles of B, they are in equilibrium with C of C and D of D, and you does you did something in the reaction where you increased the amount of A. Now you want to undo this effect. What that means is that you should move the equilibrium in a direction such that you have less A. In other words, you will tend to use up that A and move in the forward direction. As simple as that. So again, realize the direction that the reaction will take is going to depend in the direction that will reduce this stress, that will reduce this change, this new change that has been brought about. All right, so we are going to take a look at a wide variety of methods for the Le Chatelier principle, and the first one is changes in concentration. So what would happen if you add or remove a certain reactant or a product? You can do it either way. So if the concentration stress, the change has been that we have added a reactant, much the same way as I showed you the genetic reaction of adding A, and I said that it will move in a direction to undo the effect. What that means is that it would tend to use up that reactant, and hence it would move to consume that added substance, and hence in that case I showed you that it was the forward direction. On the other hand, if you add a product to a certain reaction, that would mean that in order to undo that change, that stress, it will have to move in the backward direction. In that case, just as an example, let's say you have N2O4 and it's in equilibrium with 2 moles of NO2. Okay, now by some means, suppose you add more and more of NO2. So it was in equilibrium. So when it was in equilibrium, you know that the reaction quotient is going to be equal to equilibrium constant. And now I added the product Don't you think by adding the product, I'm basically saying that Q is going to be more than K because the amount of product is going to be more than N2O4, because realize this is how you calculate Q, right? NO2, square of that, N2O4. So what we are saying is that since equilibrium constant has a constant value, Q, the reaction quotient, is going to change, and since that is going to be more than K now, it will move in a direction which is to undo that effect, to use up that NO2. It's going to move in the backward direction. So realize that the reason why this movement occurs is because you tweak, you change the value of the reaction quotient, and hence the reaction shifts to the left hand side or in the backward direction to establish or re-establish the new equilibrium. Let's revisit this reaction, the N2O4 reaction. N2O4 gaseous and equilibrium with NO2 gaseous. And suppose you're plotting concentration versus time. And basically you had achieved an equilibrium state where the concentrations were pretty much constant. You had more of the product and less of the N2O4, less of the reactant remaining. Okay, and now all of a sudden you decide to change the concentration. So at time, I don't know, maybe 5, at that particular time you decided to increase the concentration of N2O4. What would that happen? That would happen that or what would happen then? What does that mean? That basically means that you are going to have a new equilibrium setup where, because of the increase of the amount of NO2, essentially the backward reaction has triggered off. NO2 becomes your reactant, so the concentration is going to start going down. On the other hand, N2O4 is the product, so the concentration is going to start going up until it becomes a new constant. So notice a slight jump, and then this one decreases, this one increases. If you continue to do that, so if you slowly add a little bit more of the product, eventually you will have kind of like this ladder like behavior, but each time the reaction is going to reset itself to get a new equilibrium constant. If on the other hand you would have varied, let's say N2O4, so here was N2O4 and here was NO2, and you increased this, right? What that means is that it's going to decrease and then become a constant, and NO2 is going to increase and then become a constant. So the idea is still the same. It's going to be a new equilibrium that's going to be reset at a new time, unlike what it was prior to. So realize new concentrations, new time, new equilibrium will be set for this new scenario. Alright, the question at this hour is: consider the equilibrium for the water-gas shift reaction. CO plus H2O gives you CO2 plus H2. Using Le Chatelier principle, you have to predict how the concentration of H2 will change, so whether it will increase or decrease. So H2 is a product. So if H2 increases, means more products are forming. If H2 decreases, that means more reactants are forming. So that means it's the backward reaction. And this means it's a forward reaction. Alright, what direction will the reaction flow when the equilibrium is disturbed? By adding CO2. So you add CO2. What does that mean? That means that the forward reaction proceed. That means the amount of H2 should increase. If you add CO2, on the other hand, backward reaction should occur. H2 should decrease. Because realize it has to move in the direction to undo that effect. So if you have added CO2, it's going to move in a direction to use up that added CO2. Likewise, if you remove water, how can you remove water? You can remove water by using a desiccant or remove CO2. You can do that by putting some KOH chips So if you remove water, so we are removing water. What does that mean? That means that it should be a backward reaction that should take place, because we would want to then form water, and that means that concentration of hydrogen gas should decrease. Likewise, if you're removing CO2, so we are removing CO2, meaning a forward reaction should proceed, and if CO2 is getting formed alongside, hydrogen is going to get generated as well. Alright, another question is, in the following reaction, if I take away CO, which direction will the reaction proceed to equilibrium? Towards the products or towards the reactants? And hopefully you can see that it will be the forward reaction. If you're removing CO2, then more and more of the reactants are going to react with each other to generate your products. So it'll be towards the right hand side. Alright, let's take a look at the Le Chatelier principle, but now through changes in pressure and volume. And so recall from Boyle's law that if you increase the pressure, you can do that by changing the volume. So you can reduce the volume, and that will bring about a change in pressure, because you would basically be increasing by by increasing the pressure. If pressure increases, you are saying that you are going to decrease the volume. So what that means is that the number of moles per unit volume is going to increase. That's why we would see more and more collisions, and hopefully the formation of the product. So realize that the decrease in pressure, so if pressure decreases, the volume has to enlarge, volume has to increase, and what that means is that the volume density, or the number of moles per unit volume, is going to reduce. So depending on how you are changing the molecular density, whether you're increasing or decreasing the volume, the equilibrium is going to move in a direction to undo that effect. So if you increase the pressure, essentially it's going to move in a direction where there are lesser number of moles of the gas. On the other hand, since decreasing the pressure means the number of molecules per unit volume is going to decrease, that means the equilibrium is going to shift in a direction that's reflective of an increase in the number of moles of gas. So let's see if we can put things in perspective. Another problem. The question is, which direction will the equilibrium flow if the following equilibria is subjected to an increase in pressure by decreasing the volume? So we are decreasing the volume. Notice in this case, the first one, you have equal number of moles on either side of the equation. So a change in pressure is not going to have a change in the molecular density, and hence no change would be seen. On the other hand, if you consider the second case, in which case you have 2 moles on the reactant side, of course the solid carbon is not going to participate, the CO2 gas would. So now if you are increasing pressure, that means the equilibrium will move to the direction to undo this effect, and that means it will be in a direction where you have less number of moles, in other words, forward direction. And on the other hand, if you consider the last one, where you have NO2 as your product and N2O4 as your reactant, you can say that since you have 2 moles in the product side, only 1 mole on the reactant side, you're going to, as you increase the pressure and you're increasing the number of moles per unit volume, it should move in a direction to undo this effect, and so in that case it will be the backward reaction that takes place. Alright, another one. If I increase the pressure by decreasing the volume, which direction will the reaction flow to reach the equilibrium? So realize I have 2 moles on the product side, I have only one. On the reactant side, you're increasing the pressure. That means you're increasing the number of moles per unit volume, so it should move in a direction to undo this effect. That means backward reaction will be more predominant. Okay, let's try another one. Let's say if we have CaCO3, calcium carbonate, and it's in equilibrium with calcium oxide and CO2. Okay, and the question is, if you add CO2, which direction would the equilibrium move in? And hopefully you can see that if you're adding a product, the equilibrium is going to move in the backward direction to undo that effect. So if you add CO2, that means it will be a backward reaction. On the other hand, let's say I add the reactant. So if I add CaCO3, realize that if I add CaCO3, since it's a solid, I won't be making a change in the concentration, right? Because solids and liquids do not participate in the equilibrium. So no change in the equilibrium will be seen in this particular case. So it's only gases and aqueous which will count. Addition of additional CaCO3 will have no effect on the position of the equilibrium. Solids are not included in the equilibrium expression. Okay? Alright, let's try another one. How about I have 2 KClO3, and that's an equilibrium with 2 KCl and 3 O2. That's the balanced equation. Okay, and the question is, what is the effect of decreasing the volume? So I'm decreasing the volume. What is the effect on equilibrium? What is the effect on increasing the volume? Because the pressure is going to change, the number of moles per unit volume is going to change. And what is the effect of adding an inert gas? Okay, those are the three things we have to evaluate. Let's see how we'll go about it. Now, if you think about it, decreasing the volume implies that you're going to increase the pressure, you're going to increase the number of moles per unit volume. Now, you have 0 moles that participated in equilibrium. You have 3 moles that participate in the equilibrium on the product side. So if you are going to decrease the volume, that is basically going to increase the number of moles per unit volume, and that would mean the equilibrium should move in a direction to undo that effect. That means it should move towards the reactants. It should be the backward reaction which will be more predominant. On the other hand, if you increase the volume, that means you are expanding, you are decreasing the pressure. That means you're reducing the number of moles per unit volume, implies you're going to go in the forward direction. And if you add an inert gas, adding an inert gas is not going to do anything, so that will have no effect. So if you're increasing the pressure of the system, because realize pressure is due to the collisions, it can be increased either by increasing the nature of a gas, and if it participates in the reaction, it's going to matter. But if it doesn't participate in the equilibrium, it doesn't participate in the reaction, it's not going to give you any fruitful products anyways, right? So increase of the pressure is going to give you and going to change the equilibrium in a manner if and only if it is in correlation with the factors that are going to change the outcome of the reaction. That's pertinent. Okay, so let's take a look at the last factor, which is the effect of temperature change on equilibrium. Now, before we actually go over how that's going to vary, I just want you to remember from General Chemistry 1 that the delta H, which is the enthalpy of a system, let's just write it again, enthalpy If that number is a negative value, that basically means that it's an exothermic reaction. On the other hand, if it's a positive value, that means it's going to be an endothermic reaction. So in general, it is seen that equilibrium constant for an exothermic reaction decreases as the temperature increases, and for an endothermic reaction, it increases as the temperature increases. And also realize that we are looking at the delta H0 value. The 0 is for standard condition. That means most stable steady state conditions is what we are referring to. But why do we see that? In order to understand, you have to consider an exothermic reaction that you have, let's say, A and B reacting with each other, giving you C plus D plus heat. Because guess what? Heat is evolved in the system. Likewise, if you look at an endothermic reaction, you would say A plus B plus heat as a reactant. It's going to generate C and D. So now for an exothermic reaction, if you're saying that you're increasing the pressure, that basically means that you are providing more heat. What does that mean? That means that backward reaction should get triggered off. On the other hand, if you're considering a reaction which is endothermic and you're heating it, that means heat is a reactant, more and more products will be formed. Just as a very basic example, you can perhaps envision that water, liquid, phase transitioning with water, gas, and if you continue to heat the reaction, which is an endothermic process really, and you heat the reaction, more and more liquid water is going to form gaseous water. So it's going to get facilitated because it's an endothermic reaction supported by the presence of heat. So according to Le Chatelier principle, what that states is that if temperature of a system at equilibrium is changed, then the system will shift in a direction to counter that change. That means if heat is added to an equilibrium mixture, heat being added means temperature being risen. The overall reaction is going to go in a direction to relieve that stress. And so like I explained a couple minutes ago, for endothermic reaction, heat is absorbed, so forward reaction will take place, K will increase. On the other hand, for exothermic reaction, heat is given off, is a reverse reaction which will absorb the reaction. So realize that if the forward is exo, backward is endo. And so A to B. And so if the forward reaction is exothermic and you continue to increase the temperature, that means that heat is being absorbed by the backward reaction, and so the overall reaction would flow to the left-hand side. All right. The question is, when air is heated at very high temperatures in an automobile engine, the air pollutant nitric oxide is produced. So that's the reaction. How does the equilibrium amount of NO vary? So is it going to increase or decrease with an increase in temperature? Notice the thing that you should begin with is its temperature. First things to check is enthalpy. Notice if it's a positive sign or negative sign. The fact that you have a positive sign here tells you that this is an endothermic reaction. So you must increase the temperature in order to get it to go in a forward direction. So your NO amount should increase because forward reaction will take place. Will take place. What direction is the net reaction flowing? Like I said already, it's the forward reaction which the net reaction is going to flow towards. All right, let's then take a look at effect of catalyst on equilibrium. So a catalyst basically increases the rate of the reaction, and it does so by decreasing the activation energy. So it lowers the activation energy of the pathway for conversion of the reactants or products. Turns out that since there is a forward reaction and a backward reaction, and they basically pass through the same transition state, yes, we are talking about this part, so the same transition state, essentially a catalyst lowers the activation energy for both the forward reaction as well as the backward reaction, and basically by the same factor. So it will accelerate the rate at which the equilibrium is achieved, but it doesn't quite affect the composition of the reaction mixture. So you will be able to achieve the reaction faster, but how much you're going to get is not going to get affected by equilibrium. Show you graphically, I'm showing you here the reactants and the products. Notice my presence of catalyst that decreased the activation energy, but it did so for both the sides, for the forward reaction as well as for the backward reaction. So overall, all you can say is that the presence of catalyst allowed for achieving your aim quickly, but nothing beyond that. Okay. Let's take a look. Let's see if we can apply all of these principles kind of together on a problem. A platinum catalyst is used in automobile catalytic converters to hasten the oxidation of carbon monoxide. 2CO plus oxygen gives you 2CO2. Delta H is given to be minus 566 kilojoules. Suppose that you have a reaction vessel containing an equilibrium mixture. Will the amount of CO increase, decrease, or remain the same when a platinum catalyst is added, the temperature is added, the pressure is increased by decreasing the volume, pressure is increased by adding argon gas, pressure is increased by adding oxygen gas? So we have to take a look at each of these. So the first one is that a platinum catalyst is added, and realize a catalyst is going to affect the forward reaction and the backward reaction by the same amount. So no effect will be seen, no overall effect, no overall effect. We already discussed this like in the last slide. The temperature is increased. How do I, or what can be commented? The delta H is negative. That means it's an exothermic reaction. So if you increase the temperature, that means basically you're providing more heat. That means backward reaction will take place. And if backward reaction takes place, then the amount of CO will increase. The CO will increase, or backward reaction. The pressure is increased by decreasing the volume. Pressure is increased by decreasing the volume. So increase in pressure means you're decreasing the volume, means you're increasing the number of moles per unit volume. So notice there are 3 on the reactant side, 2 on the product side, and this is going to move in a direction to undo the effect. So it should go in the forward direction, and that means that CO should be used up. It should decrease. The pressure is increased by adding argon gas. Argon doesn't participate in this reaction, so that's like adding an inert gas, and so no effect should be seen. No effect. And the pressure is increased by adding oxygen gas. So we are adding oxygen, which is also one of the reactants. That means again forward reaction is going to take place because we want to use up the oxygen gas added. That means CO should decrease again. Now, this is something that we discussed earlier as well, but if you had a generic reaction where A moles of A react with B moles of B to give you C moles of C and D moles of D, and they are all in equilibrium. And if we are saying that, let's say each A, B, C, and D, the moles are 1. So your reaction is simplified to be A plus B gives you C plus D. Okay. Now, if we consider that this reaction takes place in a single bimolecular step, that means both A and B are involved and both C and D are involved as well, then of course you can say that the rate for the forward reaction is going to be rate equals Kf raised to the power of or a to the power of 1, b to the power of 1 as well. And likewise for the forward, for the reverse reaction, you will say that k reverse is equal to, or k reverse times c times d is going to be equal to the rate of the reverse reaction. Now, of course, in the beginning, there is no concentration of C and D, so there will be no reverse reaction. The reverse reaction doesn't actually exist, and it's only as time builds up, as that concentration builds up, that those actually come into play. But you know that at equilibrium, remember that curve where reactants decrease, products increase, and when they become constant, we say equilibrium has been hit. That means the Kf times A times B is going to be equal to Kr times C times D. What does that mean? That means that rate of forward is going to become equal to rate of the backward reaction. We've seen that in chapter 3. And if that is true, so just rearranging these, one can say Kf over Kr is going to be equal to C times D divided by A times B. But guess what? According to law of mass action, this is nothing but capital K for concentration. And so if you knew the rate constants for the forward reaction and the backward reaction, you can actually determine the equilibrium constant from there directly. Okay, let's see if we can actually apply that. The question is, the nitric oxide emitted from the engines of supersonic transport planes can contribute to the destruction of stratospheric ozone. And the equation is given. This reaction is highly exothermic, so that value is given as well. And its equilibrium constant Kc is 3.4 times 10 to the power of 34 at 300 Kelvin. Which rate constant is larger, Kf or Kr? It's pertinent to say that Kf over Kr is equal to capital K. And if capital K is 3.4 times 10 to the power of 34, obviously the numerator will have to be large. So you would say the Kf is going to be large at this given temperature. The value of Kf at 300 Kelvin is 8.5 times 10 to the 6th. What is the value of Kr at the same temperature? So that's pretty simple. We are going to just plug and chug 8.5 times 10 to the 6th over Kr is equal to 3.4 times 10 to the 34th, and then solve for Kr. So Kr is going to be equal to 8.5 times 10 to the power of 6 divided by 3.4 times 10 to the power of 34. And that's going to give you approximately 3 times 10 to the negative, it was 6, yeah, 28. Really tiny value. A typical temperature in the stratosphere is 230. Do the values of Kf, Kr, and Kc increase or decrease when the temperature is lowered from 300 to 230? Realize that since the reaction is an exothermic reaction, and if you decrease the temperature, so if it's an exothermic reaction and you decrease the temperature, if you decrease temperature, that's a good thing, right? So more of forward reaction will take place. That means the K is going to be higher. If K is higher, you can say Kf is going to be high as well, and that would mean Kr would fall down. If I increase the temperature of a reaction, which way will the reaction flow to the equilibrium? So this is the opposite backward reaction of what you saw in the previous case. It's now an endothermic reaction, and we are saying that we are going to increase the temperature. So if you increase the temperature for an endothermic reaction, it's going to be in the forward direction because heat is going to be your reactant. So more of the products are going to get generated.